Hi everyone, my name is Darko Pracic and I'm the environment art lead at Embark Studios. This presentation is about how we create landscapes at Embark for HIVE using Houdini. I held this presentation yesterday as an Epic sponsored talk, so I'm sorry if you were there, you're gonna hear the exact same thing. So let's see, the agenda. Introduction was done by Eric, and the next part is the background. I'll talk about our general needs as a studio. Eric kind of did the same thing, so it'll be similar. What the current landscape tools and workflows look like, and list our implemented improvements for enabling any artist to create realistic landscapes with ease. Then we go in depth. The first part is about how we treat and work with Lidar and real-world data. And the second part will be about the everyday tools in Houdini for when artists work on landscapes. And lastly, a short conclusion. So the background. Going into the background section of this presentation, we need to see what our needs are as a studio and what steps we should take to get to a position where anyone can create landscapes. More specifically, anyone can create realistic landscapes. First, we're making free-to-play games as service. This means that we want to give our players frequent content drops and expand and deepen our game over time. We should be able to reshape several square kilometers in a short time span. Second, our studio aims for realistic high-end visuals. We love pushing quality to the next level, but that will of course influence production time. Our landscape workflows have to encompass everything from grand vistas in arc radars and smaller parks in the finals. It's important that both micro and macro tasks are simplified and automated. Any artist should be able to use our tools effectively and efficiently. Third, we want to say small. Our projects will max out at around 100 to 120 people per project. Each individual should be a T-shaped developer. In other larger studios, you'll have a specific team for landscape creation, and yet another team for vegetation, and yet another team for architecture. At Embark, each artist must be able to contribute in several of those fields. And like Eric mentioned, like with a hard asset processor, concept artist, tech artist, anyone can suddenly make props, and I want to do the same thing for environment art and landscapes. Lastly, iteration times need to be as fast as possible. Our projects evolve and expand quickly. Whichever workflow we choose, it should easily abide to design or art direction changes and deliver updates post-haste. So, how have we been making landscapes previously? Let's take a look at a few of the traditional tools and workflows. First, we have the landscape-specific DCC tools. They give artists a fair amount of power, but are difficult to work with. The next point seems minor, but matters from a UX point of view. Previous landscape workflows would involve processes and filters on a two-dimensional height field. We believe that transforming and shaping landscapes is more intuitive when done in a 3D context with gizmos and handles that artists are used to from other 3D applications. And then I'll talk about why Lidar and real-world data are key to fast production when it comes to realistic landscapes, and why it currently isn't as fast as it should be for high-end games. The biggest factor is the steep learning curve for highly technical geospatial applications, which are often required when processing high-resolution Lidar and imagery. Let's go into some details when it comes to the current landscape DCC tools. Our landscape artists have been using the traditional landscape tools for years, and they are great in plenty aspects. They're powerful in what they do. They are often very well optimized, and in some cases you can even see real-time results while adjusting a slider, which is great. You're often working with large landscapes, which of course is a lot of data, and being able to process that quickly allows you to iterate more. Another nice aspect is their erosion models. If you do become a master at the tool and you're an artist with a good sense for what looks realistic, then you can achieve satisfactory results. And we're actually, for the erosion model stuff, we're actually using the Gaia bridge that Side Effects Labs has built. And I'll talk about that more later. So yet another nice thing about some of these applications, like World Creator and Instant Terra, they also have an Unreal Engine plugin that allows you to send their data to Unreal directly. Let's talk about why we feel that we want to move away from those traditional methods. Landscape tools come with a few problems. Attempts to recreate reality through generative methods are likely to fail. Adding a landscape DCC to our toolset will add yet another software that our artists have to master. And we also don't want to invest in a very narrow software. And the lack of scriptability doesn't mesh well with our goals for automation. So while we strive for realism in our games at Embark, and historically it has proven to be difficult to achieve a realistic and believable result with traditional landscape tools. Here we have an example of a piece made with Gaia, and it is believable at a glance, but the artist probably had to understand a multitude of node parameters and filters and erosion settings, and they would still be fighting an uphill battle with trying to replicate something organic and natural. These tools get their output strictly from a mixture between pseudo-randomness like noises and simulations like erosion. Using only those methods, it's of course very difficult or perhaps even impossible to fully capture what happens in reality where landscapes are shaped by myriad of factors over millions or even billions of years in highly intricate ways. One more reason for wanting to move away from utilizing a traditional landscape tool is that we want to reduce the amount of software our artists have to learn and master. Since we're already using Houdini for photogrammetry and destruction and several other workflows at Embark, most artists are accustomed to the interface and manage to do basic tasks. We only need to focus on making the landscape tools in Houdini intuitive in a way that artists only have to use it at a surface level. Also, one of our passions is to release our tools and findings to the public, open sourced, and that becomes trickier when your process involves many licensed products. The third reason for not using traditional landscape tools is that we'd like our applications to fill as many purposes as possible. And landscape tools are only built for one thing. At Embark, two of our main tools are Blender and Houdini. And those two applications combined provide a large content production platform. They are used by 3D artists, environment artists, VFX artists, character artists, and animators. Here's an example of why it's nice to have a landscape tool that can do other tasks as well. We wanted to try out a new look for our in-game map for our creators. And it was easy to send our gameplay location from Unreal into Houdini and combine it with the height field that we're working with for the landscape. And then utilize Houdini's rendering to generate a nicely rendered orthographic image with Karma XPU. After which, one of our concept artists could do their work and give it that old black and white satellite image look. Another production example, we could take the height field that we had in Houdini and convert it into a mesh with baked textures that is used in our front end, actually. Being able to convert our entire landscape that we build our world with into a simple 3D prop complete with texture baking and all in the same applications is very valuable. And the final important reason for us to move away from landscape-specific DCCs is their lack of scriptability. They're difficult to make plugins for, and you can't easily place them in any pipeline or workflow without friction. Automation is extremely important to us. We want to automate any and every step that we can, since our artists should be allowed to focus their time on being creative and working on the things that matter to players. Next is the subject of the struggles artists face when working with the two-dimensionality of traditional tools. Traditionally, when artists work on landscapes, they are working in a 2D context, and how they manipulate the landscape will often be by dragging sliders or inputting numbers or drawing out masks in a top-down 2D view. What we want to do is give the artist the same manipulation tools that they're used to from other 3D applications. A move gizmo and a rotation gizmo for starters. And anything extra that we add should at least follow a common language that they're used to from Blender or Unreal. Like I mentioned previously, this might feel minor, but our artists were able to shape and reshape our game world in our creators in a much more intuitive manner and do things that we previously had no idea how to solve. As soon as we added tools to manipulate landscapes as 3D objects, everything fell into place and we could shape the world as we pleased. I will showcase later in this presentation how exactly we shape the landscape in this 3D way. So the probably most important aspect to previous workflows when it comes to achieving realism is Lidar and real-world data. Lidar is a technology used to create high-resolution models of ground elevation. This technique has been absolutely essential for us when striving for realism, just in the same way that photogrammetry has been a standard practice for studios and artists that want to create realistic nature assets. When looking at nature asset creation, then photogrammetry is an obvious solution. You wouldn't sculpt a rock, would you? Both from the aspect of how hard it is to match reality, but also from the aspect of how long it would even take, even if you were the best sculptor of realistic rocks in the world. So the exact same logic applies to landscapes. Trying to generate or sculpt realistic features is a no-go for us. If we look at this image, for instance, it's a section of a Lidar dataset from the Grand Canyon. The terrain we see here is believable right out of the box because it is the real thing. Now, of course, looks aren't everything. We need to build landscapes that are traversable and are technically feasible. But a sensible workflow would be to start off with real-world base. Then you do the large-scale level design changes to make it work for gameplay. And then when you have the rough gameplay edits ready, you can replace those features with matching real-world ones and get the best of both worlds. Let's look at what the Lidar data actually is, and then we'll talk about one of the popular GIS applications that you'd use to work with data. If we look at this image, what you see are the points that the Lidar system will gather into a point cloud representing the ranged surface. For geographical Lidar, it's often gathered with an airborne system, with an airplane shooting a laser towards the ground and measuring how long it takes the laser to bounce back. Depending on the intervals, you'll get a dense or a sparse point cloud. When we look for data sets online, we try to find those that are at least 1 point per meter. Here we see one of the products that you can derive from Lidar, which is called DEM, a digital elevation model. It's basically a grid of rows and columns that build up the surface. If you would download the DEM product, it would be a GeoTIFF file that will also contain metadata, like the Lidar points also have. I'll talk later how we read those Lidar points in. It's with the Lidar import node in Houdini. Whoa, there we go. Let's see. In this image, we can see an example of a geographic information system application, GIS for short. In this case, it's an open source application called QGIS, which we still use in some rare cases, but I've recently put some time into automating away those steps as well by simple Python and command line scripts that we can run from Houdini directly. We don't want artists to have to learn this software, but the main benefits of it is that you can easily layer different data sets and imagery on top of each other and having a different map projection model. So yeah, here's a short list on what some of the points we have to cover if we want to reach our goals for realistic landscape creation. Processing Lidar is quite cumbersome, slow, and requires a bunch of knowledge that you will never need in any other aspect of game development. This should be fully automated. The only manual job the artists have to do is to actually find the data they want, and of course make sure it's under a Creative Commons license and free to use. The GIF shows you how easy it is for someone to initiate a Lidar data conversion for a usable asset. The artist clicks one shelf button, picks the folder with the Lidar dataset and they want to process and press OK, and then a PDG process will spawn automatically and start cooking, converting those files into usable height field assets as BGO files. More on this soon. Next, we need tools and utilities to enable the artist to adjust, mix, and manipulate Lidar-based height field assets in Houdini without compromising the quality. A couple of them would be the height field lattice HDA that we've made, which allows artists to transform their height fields with ease as 3D objects. It actually converts the height field into a polygon mesh that we then reproject to the height field. And then we also need a way to procedurally generate believable colors. Previous workflows involved a lot of manual work trying to calibrate the colors of an 8-bit satellite image and try to remove buildings and vegetation and shadows and lighting. That was a complete nightmare. And that's one of those cases where we actually have to figure out a generative model unless someone has a way or a product that is completely de-lit and no buildings, no bushes, etc. We also need ways of creating interesting masks for our landscape materials in Unreal Engine. Getting a wide range of masking and distortion features will be critical to make masks that don't pop out as looking generated. And lastly, the export and import. Currently, we're not near where we'd like to be. I would prefer us to be at a state that like World Creator and Instant Terra is, where we have a plugin or a bridge where you can just send the data. But currently we have an interface where the artist picks the tiles they want to export and the layers that they want to export. And yeah, you can also export the entire tile set. So on to some actual Houdini tools. And our first main section will be about our Lidar processing and our first implementation of an asset browser. So there are 3 main processes that we need to automate, and it's when you download the Lidar, usually you download LAS or LAZ file. So that process we've finalized. We use the Lidar import and a PDG process that converts that into HIVE fields. But then you can also find data sets as GeoTIFF files, like the digital elevation model, ready as TIFF files. That we haven't done yet, and that's my next goal. And then we also haven't done where you find different data sets. So maybe you find a high elevation data set at some place, and then we found a nice imagery data set from another place. Those need to be aligned, and their map projection needs to be matched, and you need an output. So that I've started to use QGIS as a what do you call it? As an intermediate step where I can script QGIS, read in those data sets, get them to match up, and then export the extent with the same projection model. So what the goal with all of this is to get your data set as usable assets in Houdini, much in the same way as you have megascans in Unreal, where the artists can just be creative and just drag in nice looking content that looks real into their scenes. And we want to have the same thing for Lidar datasets. So what we've done so far is to automate sourcing the data from various sites like Open Topography or USGS, and other nations have their own geospatial survey sites like Spain or Norway that have free data. So we want to gather that data from those sites, and they can provide you often with FTP servers or lists where you can batch download everything with a script as well. So this asset browser thing is just a Photoshop mockup. We haven't had the time yet to build. We have an asset browser, but not like something where you see the assets. But I guess it should just be to write ask ChatGPT to write a PyQt5 asset browser. I recently learned that you're not allowed to use ChatGPT for code and use it in your company, so I won't do that. But still, the main idea is for us to be able to grab processed Lidar assets and inject it into our landscapes, like so. So here we see the main PDG network that will read in the Lidar files, convert them to high-resolution height fields, and save them on disk. Then it will take those files and resample them to a much lower resolution and save those on disk. The reason for that is that we need a way for artists to quickly preview things. Loading in the high-res height fields is incredibly slow. So we output the low-res files, and then further down in the PDG process, we import them back in and merge them. and output another height field that is the entire data set in a low resolution format that you can review in real time in the viewport. So here's an example of what a complete data set like that looks like of Tenerife, which we use a lot in our creators. So the main node that we use in that process is the Lidar import, and I don't know when, but it recently got upgraded where you can get all, maybe not recently, but I noticed that it got upgraded to read in all the classification filters for buildings and vegetation, which we can then use for masks. Sorry? 5 minutes. Okay. The import Lidar points get transferred onto a height field with volume from attribute sub. And this is the first iteration of our asset browser for our Lidar content. You click a shelf button and wait. And the list will dynamically be populated by the available assets on our network location. So here's an example of that. We read in the dataset, and this preview mesh is 56 million points. The high-res dataset is 2.5 billion points, and being able to read data by a lower resolution proxy is crucial. We don't want artists to be stuck in 30-minute load times and applications crashing on GPU memory. So you should always be able to work fast in a lower resolution mode and then get the high resolution content in loadable chunks when needed. There are even volume compression possibilities to reduce the memory cost of your loaded data, but they should be used carefully since they may introduce artifacts. Here's an example of a few of the classifications of the Lidar dataset. You have the buildings and the low vegetation and the medium vegetation and the high. Yeah, here are the buildings again. So that was a brief look into our Lidar processing. Let's move on to our Houdini height field tools. So we're using Gaia. I mentioned that we want to move away from traditional landscape tools, but we still need a powerful erosion model until side effects improve theirs. This is a useful utility, and yeah, we didn't create this. It was Side Effects Labs. Let's see. So we needed to get nice looking deformation, and even more importantly, different masks like erosion flow and sediment deposits for our in-game landscape material masks. We will mostly rely on real-world data, but there will be cases where we need to fill the gaps with procedural solutions, and having a bridge to Gaia in Houdini fills that gap. For the masking part, we're both using standard Houdini height field masking nodes, which offer a great range of feature-based options. To supplement that, we also add some flow maps from Gaia. Using the erosion in Gaia with a very short duration will give you these nice-looking thin flow lines. Yeah, let's move on. Here's a short demonstration of how we utilize the Gaia bridge for cases when the artist has had to manually shape out a piece of the landscape. And when I was talking about like the 2D and 3D way of working, I would say that this is the 2D way of shaping a landscape where you paint, draw out masks, and like, this is fine, but it's more intuitive and explicit when you just grab the chunk and move it to the position you want. So I'm just adding some noise here, and then I will add a Gaia Tor processor that will give us a nicely eroded feature. So we can still use this. Like, we don't always have to use real-world data, and we don't want to be, locked by that or restricted by that. And I mentioned previously that we need a way to generate colors, so let's look at our current solution. On this slide, we see a few results from our height field color node, which procedurally generates colors for our landscapes. Our main goals have been to produce both large-scale variations that feel natural, but also high-frequency breakup, which is what the players will see in their near proximity. Here's an overview of the HDA. It relies on an input image, so you input like a satellite image to just convert it into a color ramp. And this is made possible by an HDA made by James Robinson. It's available on GitHub and Orbit. After that, we generate a bunch of masks with Gaia, which will be used in several of our coloring categories or layers. We have a base layer, a slope layer, a plateau layer, and a flow layer. This is just the current state, but we feel that we can go infinitely deep with this and define a multitude of features for coloring. The way we get to large-scale variations is to map a very low-frequency noise or a large-scale occlusion mask So when you have a large-scale ramp that can be, what do you call it? When you have a masked, how do you call it? A ramp? No? When you have a mask that is matched to the color ramp, you'll get these large-scale features. And to break that up, map was the word I use. We map something that has higher frequency to get those micro gradients on the color ramp. And we blend them together and we get these large variations with a detailed breakup. So on to a few of our tools that fall into the work in 3D category I mentioned earlier in this presentation. So first we locate, here's a demonstration. We locate an area of the landscape we wish to improve. So what we're looking at is about a square kilometer of gameplay area. We load our Lidar dataset that we intend to use, and we crop out the specific section that we need and load the high-res version of it, which just finds the BGO file that matched the, position. Next, we align that Lidar data with our height field align node, which is using viewer states, where you can just easily drag the piece around and rotate it and scale it. And to make the shapes fit more neatly, we use our HDA, lattice HDA that I mentioned, and this allows us full 3D control of the landscape. So here at the end, I compare the end results in high-res. When we're working with all of this stuff, I set it in the viewer state to automatically resample, so you can work faster. You have a real time. So let's take a look at what it looks like inside Unreal. So that's the end result. And next, I want to mention just a few of our Houdini engine assets that are height field or landscape input based. The first one is our height field cliffs tool, which, you place the HDA in the world, input the landscape, and it will generate a surface along the slope. You have a slope mask, and then it will displace it with a tile-built texture, reduce the mesh. We also have features where it cuts up it into smaller chunks and also cuts up the collisions into smaller chunks. It was actually related to our machine learning enemies, where large bounding volumes would be really expensive for the machine learning to trace. So we had to chunk this up a lot more. So let's take a look at another video because I'm quite happy with it. And it doesn't cook that fast. I've sped it up by a lot. But works quite all right. So let's take a look at another Houdini engine asset. So we need to generate far LODs for our landscapes when the levels stream out. Our world is using world composition. We haven't yet upgraded to or switched to world partition, but I guess it's the same setup. Our world is 64 tiles, and when you move away, it will stream in the LOD level. And we wanted a way to generate nice-looking landscape LODs. So same way, we read in the landscape into the HDA, and we cook and we build a material inside of the Houdini asset as well to match the materials. But the Houdini engine asset will also read in all the landscape layers as well. So we use that to mask out between different materials. And bake the normal maps with the maps baker, side effects, maps baker. So at a distance, we feel it's satisfactory. Conclusion, we have some things in place. It is much easier for artists to build landscapes with our current tools, but these are just the first steps of a bigger journey. We've gone from having work files that take 30 minutes to just sync and perforce, and then 30 minutes to open them, to being able to reshape several square kilometers with highly realistic data and have that in-game within 30 minutes. We also gone from a point where we would have to be satisfied with the base LiDAR data and try not to alter it, because that could ruin the features, to a position where we can both alter it to our visual liking, but also, more importantly, adjust any area to gameplay requirements as well. It has to play well. That's the most important part. So I'm going to end this presentation with a video montage of the world we've created for our creators. Thank you.